Sorry about that. I have this bad habit of trying to fill up 15 minutes just because the software lets me go to 15 minutes. I really don't mean to do that. So I promise I won't go to 15 again. This won't be a 30-minute video on one section. That'd be really bad. Okay, so we just got to the point where we got expected values to be 7. And expected values don't always turn out to be so nice. I mean, this one turned out to be 7, which also happened to be the median. Remember, this is such a symmetrical thing anyway. Maybe that's not such a surprise. But there could be ones like, we had the one about Michael Jordan and the free throws on the last worksheet. It could come out to be something weird, like what's the probability that he's going to make 3 free throws in a row or make 2 out of 3 or something like that? Or actually, it would be more like this. What is his expected number that he should make every 3? And it's something like 2.73 out of every 3, which isn't a real possibility. You can't make 2.73 free throws out of 3. Just kind of like, you've heard these stats before, this, because this is an average. Just like you can't have, 2.4 children. You've heard that stat for a long time, because the average family isn't a real family. The average family is a statistic. It's about, sort of if you were to take everybody into account and divide by the number of families, this is how many children each family has, which doesn't really tell you much. It kind of tells you that there are sort of the average family, or people who are close to being average might have 2 or might have 3, and there's sort of more families that might have 2 than 3, sort of, that pull that average down below 2.5. And it's somewhere between 2 and 3 and closer to 2 and that kind of thing. Or if you knew you had 10 families, you should expect there to be 24 children. Same kind of thing here. If he's going to make 2.73 shots out of 3, you could sort of multiply that up out of 100 and make another percentage out of it if you wanted to, and that kind of thing. All right, so back to our 3 coins. What's the expected value for the number of heads you should get when you toss 3 coins? Well, on the other page there, we talked about how the probability of getting 0 is 1 out of 8, 1 is 3 out of 8, 2 is 3 out of 8, and 3 is 1 out of 8. For this calculation, you just kind of do the same thing. Expected value, and there's a symbol for that. It's pronounced mu. The expected value, when you're just saying, okay, I'm going to toss 3 coins, how many heads should I expect there to be there? Well, I take 1/8 times the possibility that there could be 0. I'm kind of doing this backwards, but it fits the way I'm saying it, and it's going to be the same end calculation. Just multiply them backwards. There's a 3/8 chance that I'll get exactly 1 of those to be heads. There's a 3/8 chance, so I'm basically going to add in sort of 3/8 of a head there. There's a 3/8 chance that it's going to be 2. So here I'm adding in kind of like 3/8 of 2 heads, because that could have just as easily come up. And there's a 1/8 chance, so I get an 1/8 of 3 added in here. I get a 1/8 chance that I'm going to have all 3 heads show up. All that factors into sort of this big theoretical average. And I kind of like the way I just said it there. There's a 1/8 chance there's not going to be any. So 1/8 of the time, forget it, you're not getting any heads. 3/8 of the time, you're going to get 1. So that kind of counts as 1 of those 3/8 copies. 3/8 of the time, I'm also going to get 2. So I'm going to get 1 or 2, kind of a lot, and one head 3/8 of the time, 2 heads 3/8 of the time. But there's also 1/8 of the time I'm going to get all 3. So that should add in sort of really heavy for that 1/8. All right, so if I add all this up, you notice I get 3/8 plus 6/8 plus, well, I should add that up. Add these up in eighths. 3/8 plus 6/8. The zero's gone, so it doesn't add to anything, plus another 3/8 adds up to 12/8. Which, now this isn't a probability, so don't let this alarm you that it's bigger than 1. We've had a lot of fractions this chapter that have had been less than 1. This is expected value now. This isn't probability, so it's perfectly fine for this to turn out to be 1.5. Now, I don't know, maybe this doesn't surprise you either, that if we toss 3 coins, and each one sort of has half of a probability of turning up heads, that out of 3 we should expect half of the 3 to turn out to be heads. I don't know. I don't know if it's a valid thing to make that sort of prediction. It turns out to be right here that half of those coins are going to be heads. Or when you toss 3 coins, this is a better way to say that. When you toss 3 coins, you should expect, on average, that 1.5 heads will turn up. So that's your answer to video question 2. They also have a very similar story in the book about the same situation, but it's about families with 3 kids, and there's an equal chance of having a boy and a girl. And what if you have 3 children? How many boys should you expect in 3 children? And like heads and tails, you get a decimal answer for that value of expected value of number of boys. And tossing 1.5 heads, or and this is going to be exactly the same. Having 1.5 boys isn't an actual possibility, but it's the expected value. Over lots of families, over lots of times, this should be sort of the average of the number of boys you should expect in 3. Would be 1.5. And again, I promise you, they're not always going to turn out quite so predictable and tidy. It's just these are some good examples to get you going. Speaking of not being predictable or tidy, here is the notation for mu. Yes, mu is a symbol you can actually type on the computer. It's the sum of all these probabilities. Remember, here's the one for the dice. It's the value of the random variable, sort of like the sum you record, or the number of heads, or whatever, times the probability that that thing is going to happen. And that will all add up to the total number of heads you should expect, or the total number you should see on the dice on average. Writing that out this way is sort of a big, nasty looking thing. It's our friend the sigma notation. This is the sum of all those things: the value of the expected value of the random variable at whichever location we're talking about, so like 2 or 3 or 4 on the dice, or 0 or 1 or 2 or 3 heads, times the probability that that one is going to happen. The sum of all those probabilities should be 1. The sums of these could be anything. I mean, really, the sums of these are the sums of all the different possibilities of the values of the random variable, or all the sums of all the different sums that could show up on the dice, or number of heads you could get. So that's kind of weird to think about. But this is just kind of like recording, like, what's probability I get a 2, and then so probability I get a 2 times actually 2, and the probability I roll a 3 times 3, and the probability I roll a 4 times 4, because that 4 will sort of add to the average because it's a bigger number. And we do that for all the values all the way up from 1 to n. Add those all up, and again, no dividing. I know when you see average you feel like you need to divide something, but it's already being divided here within each probability. It's sort of as a distributive measure. Notice all these, it's getting divided by 36 at every step along the way. So I've already done the internal division, and it actually is pretty simple when you think about it. It's the number on the dice times the probability that die is going to show up, or analogously similar for any other probability. To calculate mu, the expected value. Okay, said I wouldn't talk long. That's it.